So a little review, we ended with this one, the improper integral of type 1. So review, we have improper integral type 1 when one or both limits of integrations are infinity. So case 1 is when we have the upper limit as having infinity as the value. Case 2 is when we have the lower limit as the having the negative infinity value. And case 3 for type 1 wherein both limits are infinity. So we have negative infinity to positive infinity in that case. So this is where we ended last meeting. And also in the discussion, we have discussed, so this is a review, the terms convergent and divergent. So if your improper integral, wait class ha, I lack already battery. Wait lang. Okay, so I'm back. So when we speak of convergent integrals, the integral have a specific value, meaning it is existing and its value is a real number. When we speak of divergent integrals, improper integrals type 1, it does not have any value whatsoever, real value associated with it. So we say that it is divergent, or shall we say there is what we call a discontinuity in the graph of that particular function on the stipulated interval of or limits of integration. So that's uh, improper integrals of type 1. So now we go to discontinuous integrals and type 2. So if we graph the function on the interval that is the limits of your integration, we have what we call as a point of discontinuity. So let S be an unbounded region under the graph of F and above the x-axis between A and B. So for type 1 integrals, the regions extend or extended indefinitely in the horizontal direction. Here, the region is infinite in the vertical direction. So there is infinity in the vertical direction. So you could see in here, now type 2, we're talking already of type 2. Suppose f, our function, is a positive continuous function defined on the interval a to b, but has a vertical asymptote of b. So meaning class, I'd like to use our vernacular language when we speak of has a vertical asymptote, discontinuous sa sa class. So asymptotic na siya sa sininga line na x equal to b. If that is the case, we say that our function is discontinuous on this particular limit of integration, which is b. Now, the area of the part S between A to T, so this is A to T, where this T will be approaching infinitely this line x equal to B, is the one that is shaded in here. Now, our graph is said to be discontinuous, but in the sense it's discontinuous based on this vertical axis because it's asymptotic to this line x is equal to B. If that is the case, we have type 2, a discontinuous integral. Now, if it happens that a of t approaches a definite number a as t approaches b, then we say that the area of S is a, and we write that the value of this is the limit of the integral from a to t, where t is approaching a value which is b with a negative sign. I hope class this was discussed to you in the differential calculus that whenever you see a negative sign as an exponent of a number, the particular value that the variable is approaching this particular number is from the left side of the Cartesian plane. What do you mean by that, Miss Alice? If this is x equal to b, your t equal to x equal to b is being approached from the left. So halindi siya sa wala, patuo siya. That is why you have this particular sign here which is negative. If this sign is positive, then I'll go back to the graph. This x equal to b line is approached from this side class, from the right. Then it's still said to be asymptotic to this line. So if the Again, if the exponent here is negative, it means that t is being approached from the left side. If this is positive, t is being approached from the right side until it approaches the value equal to b. So we use the equation to define an improper integral of type 2 even if f is not a positive function, no matter what type of discontinuity f has at b. So let me just continue. So if f is continuous on a to b and is discontinuous at b in that case, in what I have shown to you, then the integral from a to b of your function is equal to the limit of that same function where this time your b here was changed to t and t is approaching b from the left side. If this limit exists as a finite number, then we have this particular integral in terms of the area under the curve y equal to the function of x. Now, if f is continuous on a to b and is discontinuous at a, so kaina class, ari di ang inyong line x equal to b. Subong ang inyong line, ari naman siya sa x equal to a. Now, this line x equal to a is being approached from the right side. Kaya hindi man di siya ka-approach dire kay tungod nga ang limit nimo is upper limit mo b as talang gidire and imo lower limit is a. So it has to be approached from the right side to this x equal to t value, which is approaching a. In that case, class, you see, it's already positive here because your x, which is t approaching a, is approached from the right side. I hope you understand when I say nga hindi ni siya pwede i-approach sa left side kay wala ni diri sa left side ang limit niyo nga b. Ang limit ninyo nga b ari sa right side. So it has to be approached from the right side. So if this limit exists as a finite number, that limit is the area under this curve y equal to f of x, where the limit is from t to b, where t is approaching the value a from the right side of the Cartesian plane. So again, this one is case A, because we are approaching the value x equal to b from the left side. And b is the upper limit, a is the lower limit. This one is case b, that one is case A, because we are approaching the value x equal to a from the right side, because this time it's the upper limit b which is fixed and the lower limit a which is being approached to from the right side of the Cartesian plane. So that's your case to be under improper integral of type 2. Now, the improper integral then, function of x from a to b is called convergent. We also have the term convergent and divergent for type 2 if the corresponding limit exists. So convergent if the value that you are getting out of evaluating the integral is a real number. It is divergent if the limit does not exist. So wala siya ga-exist, it is said to be divergent. Now I will continue. Let's say this example. Let's have this example. So remember, we are on improper integrals of type 2. Ano gani ang type 2? Ang may discontinuity. So let's say, for example, you have the integral of the secant of x dx. And look at the limit, it is 0 to pi over 2. So when you look at this definite integral, it's so easy to commit a mistake of saying that this is not an improper integral. Why is it so easy to commit a mistake of saying that this is not an improper integral? Because this is not type 1 wherein any of the limits here is infinity. But if you look very closely, if you're going to plot the second of x function on the interval 0 to pi over 2, which represents the limits of the integration here, you will see that there is a point of discontinuity, meaning the graph will be approaching the value either 0 or pi over 2. We don't know yet for now. Infinitely, meaning one side of your curve will be asymptotic to either x equal to 0 or x equal to pi over 2. So our infinite area here is extending vertically, not horizontally in the case of type 1, as I have mentioned a while ago. Now, note that the given integral is improper because the limit of second x approaches infinity when you substitute pi over 2 to the value of the x here. Now, if you have your calculators there with you, class, you can try. Second is 1 over cosine. So try cosine of 90 degrees. Then you invert it. The calculator will not give you an answer for that. Why? Because it's infinite. Try it. The function, when evaluated on any of these limits here, will have a discontinuity. In this case, you can substitute 90 degrees or pi over 2. Get the cosine of 90 degrees and then invert that, meaning 1 over cosine of 90 degrees. It will give you infinity because that would be division by 0, right? Did you check it? You have to have your calculator so that you will be able to relate to what I'm saying here. So if you get the cosine, because second is the reciprocal or is the inverse of the cosine, if you get the cosine of 90 degrees, that would be 0. 1 over 0, because we're talking of the second, is infinity. So as such, even though our limits is not infinity, this one is an improper integral because your function is discontinuous on one of the limits of the integration, which is pi over 2. That's what I'm trying to explain here. So if you have checked it in your calculator, you will know. So whenever it's infinity, then your function is said to be continuous, or the graph of that function is said to be not continuous but discontinuous on that particular value. So you can see here, if we will evaluate the integral, that would be the limit of the integral from 0 to t, where this t is approaching pi over 2. This t, this x here, the t is pi over 2. The answer of the second, if you recall in midterm, as what we have discussed, is the ln of the second of x plus the tangent of x. I hope you haven't forgotten yet. If you will substitute the limit 0 to t to that, the upper limit will be t. So you will change all the x here that you are seeing to t. So this is now t. And then you will substitute 0 to the second of 0 and to the tangent of 0. The tangent of 0 plus is 0, but the second of 0 is 1. That is why you get here an ln of 1. I hope that makes sense. So I will place here an annotation so you will know what I'm talking about. I'll just use a different color. This one is your upper limit. So upper. This one is for your lower limit, the ln of 1. How is this particular ln of 1, or how did ln of 1 came about? Remember that you will substitute 0 to that. So I will just place in here, that is actually ln of the second of 0 plus the tangent of 0. I'm talking about the ln of 1. This tangent of 0 class is 0. But the second of 0 is 1. So that is why you have only ln of 1, because ln of 1 plus 0 is just ln of 1. So you see this? Now, you see that these are t's. Why is it t's? Because your upper limit is t. But that t is this x which is approaching a value of 90 degrees, or that's equivalent to pi over 2. And I have shown to you a while ago that when you check in your calculator, the second of 90 degrees is infinite. This is infinite. This one. The tangent of 90 degrees is, what's the tangent of 90 degrees? Do you have your calculators there with you? Am I alone here? What's the tangent of 90 degrees? Tangent is opposite over the adjacent. What's the tangent of 90 degrees? Class, are you there? What's the tangent of 90 degrees? You don't have your calculators there with you. How can you check the values that I'm giving you? Let me check. Mr. Gamau, what's the tangent of 90 degrees? Cholo Gamau, what's the tangent of 90 degrees? Oh hala, try go pa niya. Bobby Maravilla, what's the tangent of 90 degrees?
Math error, miss. Indeterminate.
Oh, correct. Indeterminate because it's 1 divided by 0. So you see that you have now indeterminate. An ln of infinity minus an ln of 1. What's the ln of 1? If you don't have your calculators, this is right away equal to CHE, ln of 1, 0. So you have an ln of infinity, which is infinity. So this is because the second of t approaches infinity and the tangent of t approaches infinity as t is approaching pi over 2 from the left. So my question actually is being answered by this already. Thus the given integral is said to be divergent. So we have learned that if the value of your improper integral does not exist, it is said to be divergent. Okay, so this is one example of an improper integral type 2 because the limits of integrations are not infinity, but rather real values, but the function has a discontinuity on this interval. Okay, I will clear what I have here. Then we will proceed on the next slide. Okay, that's example number 4. Now, we'll have number 5. ln of x dx. What's the integral of an ln of x? This is to be processed using, anyone? We're done with midterm. The ln of x is processed using the technique of
IDT.
um, why?
By parts, miss.
Very good. It's by parts. So ln of x is processed using by parts. So I will assume that you know already what is by parts. So as to your limits here, 0 to 1, you will say, this is not an improper integral because my limits are real numbers. But if you will place again the graph, or if you will plot again the graph of this function, from 0 to 1, there will be a discontinuity. So that is why this is an improper integral. So we know that the function f of x is equal to ln of x has a vertical asymptote at 0. So meaning your point of discontinuity for this particular function is at 0. So it has a vertical asymptote at t equal to 0. So since the limit of ln x is equal to negative infinity as x approaches 0 from the right. So you see this positive. Thus, the given integral is improper. Okay, may discontinuity siya, may vertical asymptote siya. And we have the integral of the ln of x from 0 to 1 equal to the limit of the integral from 1 to t ln x dx as t approaches 0 from the right. So you can see that one. So I will proceed. And now if you integrate by parts, this is your answer. Or this is your answer actually when you do by parts. This is your answer, x ln x, and the integral of dx, which is actually, this one is equal to x. So your answer for this is x ln x minus x. That's your answer. But you have to evaluate your answer for this integral, which is this, from t to 1. Okay, t to 1. Now, if it's 1, the upper limit is 1, you just substitute 1 ln of 1. We know that this one is 0. Okay, and then for the x, which is 1, so you will have ln of 1 again. So specifically, class, if you're going to write this, you have 1 ln of 1 minus, this is actually 1. Okay, that's your upper limit. X ln x minus x. If I substitute the 1 first, this is your answer. Minus, so the lower limit, that would be t ln of t. I'll change the x to t minus t. Okay, now this one is, of course, 0. And this one is negative 1. So that's negative 1. So you see your answer. The answer here is negative t ln of t, copied from here. This one is negative, negative. That would be positive. And you have here negative 1. This is the answer to this particular integral. But notice, we still haven't yet substituted what value will t approaches to. Wala pa. Because in here, in the original integral, is 0. Okay, the t approaches 0 from the right. So it did not erase what I have written, so you can follow through in here. So this t actually is approach from the right. It's approaching a value which is equal to 0. So that is 0. So what will happen if you will place here a t which is equal to 0 and ln of 0? I will continue on the next part here, the next slide, so you would understand. So, but this one is already clear how it became. Okay, now, the limit of t ln of t is this. Now, what happened here is we are going to use L'Hopital's rule. Why do we need to use L'Hopital's rule? Anybody? Why do we need to use L'Hopital's rule in this case? Why? Because
Indeterminate siya, ma'am.
indeterminate siya. O tanawan nyo bala kung ano ginatawag nga indeterminate? 0 siya, no? ln of 0. I would just simply substitute the 0 here and ln of 0 here. The ln of 0, actually, this is equal to negative infinity. So it's like 0 times, when you see a dot, that's times negative infinity. ln of 0 is negative infinity. So when you multiply a negative infinity to 0, it's indeterminate. So what was done here is we find a way to evaluate this indeterminate expression. We call this an indeterminate expression. How? Make it, shall we say, manipulate it in such a way that it would still be equivalent to the original. How do I manipulate? So you copy ln of t. This is ln of t. And this t here, if I write it as a denominator, that would be 1 over t. This t goes up, and it would still be equal to this, right? So this one, the ln of t over 1 over t is just t ln of t. If it's now written in rational form, when you speak of rational, the fraction na siya, pwede ka na ka-L'Hopital's rule. So what is L'Hopital's rule? Differentiate the numerator and the denominator separately. So you differentiate. So if you differentiate ln of t or du, that would be du over u. So 1, get the derivative of that 1 over that thing, 1 over t. If you differentiate 1 over t, that would be negative 1 over t squared. I think I will not explain that to you because you are already in integral calculus. You know how to differentiate already. If you will cancel this, there's still 1t left here. So that 1t will go up and that would be negative t. Now what will happen? The limit of negative t as t approaches 0 from the right is 0. So from an indeterminate expression, using L'Hopital's rule, we're able to find an answer which is 0. What is this 0? That 0 is this class. We'll just erase, get the annotation. This is it. Ini siya balao, nan amo na siya ang determine ta dito sa pihak. So this is already 0. So I'll go back. This one, negative lang siya. It's 0. So now we will continue. Feel free to interrupt me if it's not clear to you, okay? Now, so we now continue. So this is negative 0 is still 0 for this one. That's negative 1 and 0. So the answer is negative 1. So see, this is an improper integral because this one does not exist. This ln of x does not exist at 0 when you plot it. But it's a convergent improper integral of type 2 because the answer to the integral is a real number. So it is convergent. Okay? Any question? Okay, I will continue if there are no questions. So the geometric representation of that particular example is this. So this is the area of the curve, or rather this is first the curve y equal to ln of x. This is your curve. Now, when you determine the integral from 0 to 1 of this particular function, ln of x, actually, it's this area that you are after, the one that is colored blue. And the value of this area is the value of the integral that we have just solved. So the value of that integral is equal to 1. So that would be our next topic, areas under the curve and areas between curves and lines. So, but nonetheless, whenever you process a definite integral, that is just like getting the area of the function of that particular integral on the designated limit. So kung ano ang limit, like this one, it's 0 to 1. This is our function ln of x. So meaning when you find the value of the definite integral, you're just finding this area. The value of that area is equal to 1. So the area of this shaded region above y equal to ln of x and below the x-axis is equal to 1. So this is that particular area of the curve. Okay? Now, we cannot, of course, determine, you may answer, Miss nga away mo na digin determine ang area di sa babaw, how away mo siya din determine. What do you think is the answer? Why did I not determine the area above here? Anybody who can tell me? We're not yet on areas. I'm just asking for curiosity's sake. Why do you think when we determine the area of ln of x from 0 to 1, we're only concerned with this area? We're not concerned with the area above the x-axis. So it says here below the x-axis. Why not consider the area above the x-axis?
Ay,
Yes.
hasta lang siya may sa 1 ng limit pa.
Very good. Kaya karon kung inibilan sa babaw, i-consider nyo ya 0 to sobra na siya sa 1, kaya astalan tayo sa 1 mo. So hindi na yan inim 1.1 na or 1.001 hasta dire. So hindi na siya yan na-include. Ang ato na yung sulbon is from 0 to 1 lang. So amo lang ni ang area nga aton nga i-determine. Wala na siya na-include ang sa babaw. Okay, but it's not yet part of our topic now. We're just simply talking about type 2 of improper integrals, convergent and divergent. Now, we have case 3. So, duwa na gid yo. If f has a discontinuity at c, where c is in between a and b. Why I say it's in between a and b? Because this c is greater than a, but is less than b. And both the integral a to C of the function and C to B of the function are convergent, then we define, and it's a property of the definite integral, that the integral of the function from A to B is equal to the integral of two separate, is equivalent to the sum of two separate integrals with the same. So I would like to annotate here. Where is that? I can't find. Oh, sorry. You can see that you have the upper limit of the first is the lower limit of the second. It's the property of the definite integral. And as such, it's just saying that you're after the integral of the function of x from A to B, just like this one. Now, if it's illustrated using a graph, so this is your lower limit A, this is your upper limit B, and this is the C in between. The C that you use as the upper limit here and the lower limit on the second. And what happens on the C? From A to C, you have this point of discontinuity. Your graph is asymptotic here. And from B to C, you also have a point of discontinuity here. So it's asymptotic also to this part of your, shall I say, x-axis, where x is equal to C. So it's an improper integral because your integral has a point of discontinuity, which is at C. Improper siya. Type 2. It is convergent if both of these improper integrals whose sum is the same as the original integral is convergent. So this is case 3. Okay, I will erase the drawing, clear the drawing, and then proceed with specific example. So we have this. Evaluate dx over x minus 1 from 0 to 3 if possible. So specific siya, no? If possible. Now, if you look at it, okay lang na siya, means hindi siya improper integral kay ang limits mo hindi infinity. But remember, excuse me, remember that when you have the limits 0 to 3, in between the 0 to 3 is 1. And if you have here 1 minus 1, your function, by the way, your function is 1 over x minus 1. So if you substitute a 1 here, that would be 1 over 0, and that would be infinity. So we say that the line x equal to 1 is a vertical asymptote of this original function of your integral dx over x minus 1 integrated from 0 to 3. So improper because there is this point of discontinuity. Now, in the first two cases for type 2, your discontinuity is either in the lower limit or in the upper limit as discussed. Sa duwa to bala ka example, ang ato nga discontinuity ari either sa lower limit or sa upper limit. Subong ara siya sa tunga-tunga. So do pariho siya sa type 1 nga ang point of discontinuity ara man in between. So you have here a vertical asymptote on the line x equal to 1. So I will clear all drawings and markings and we will proceed. As it occurs in the middle of the interval 0 to 3, so we will have the integral evaluated. Take note at that point of discontinuity or at that point where your curve is asymptotic to. So you evaluate it like this. You start with 0 to 1. You end here as the upper limit, and you start with that same limit, but this time lower limit for the second. And you have 3. This same function. Okay? When you evaluate these two functions, it's so easy to evaluate them because it would simply be an ln, right? So if we will have the 0 to 1 first, integral of dx over x minus 1, we have the limit of dx over x minus 1 from 0 to t, where t approaches 1 from the left. So you have this. The answer is the limit of x minus 1. We have here limit of x minus 1 as t approaches 1 from the left. Now, actually, class, this is not just the limit, but the limit of the ln. I lock here the ln. The ln of x minus 1. Now, we change this x to t and 0. Upper limit is t, lower limit is 0. So, limit of the ln of t minus 1 minus the ln of 0 minus 1, which is minus 1. Okay? Now, the limit of ln of 1 minus t is equal to negative infinity. Now, why interchange this one? What happened here? You have an ln of t minus 1 minus an ln of negative 1. What happened here? Why is it the limit now of the ln of 1 minus t? Why? Diri ang original nyo, ln of t minus 1. Diri ang natabo, it's the limit of the ln of 1 minus 2. What is this? Why is this like this? This is because you can see here that 1 minus t approaching 0 from the right is as t approaching 1 from the left. This is the discussion. This is because your 1 minus t approaching 0 from the right is just the same as t approaching 1 from the left. That is why this original expression that you are seeing now is just equivalent to the limit of the ln of 1 minus t. If you will substitute the ln of 1 minus t, here you substitute 1 to the t, you will have an ln. Substitute ko na ni ang 1 ha, there is a t, negative, so meaning it's approach from the left. So this would be the ln of 1 minus 1, which is a 0. The ln of 0, as pointed to you a while ago, is negative infinity. This one is negative infinity. Now, this one already, isa pa lang din check ta ha. This one already is negative infinity. So, if either of these two integrals equivalent to this one fails to exist, the original integral already is non-existing because this one already is said to be divergent. So kung ang isa lang o kung ang duha gid sa sum sang duha ka integral equivalent to the original is divergent, the original is already divergent in itself. Now, if I will erase my marking here, you will see that the said integral will be divergent. So thus, the integral of dx over x minus 1 is divergent from 0 to 1. And this implies that your original integral is also divergent. So ang iya nga question kay na mabalik tabala sa example, whenever possible, kung posible lang. Evaluate this if possible. So since it's not possible because your one of the integrals equivalent to the sum of two integrals to your original is already divergent. So it's also divergent. So this is one which we need not evaluate already. So hindi na kinahanglan i-evaluate. So ma-wonder ka, you may wonder, why is it that when I evaluate this, or if I use my calculator to evaluate this nga, hindi siya ka-answer how? It's because in the first place, it cannot be evaluated. Now, there are, however, class, there is this big question, ha? There are, however, functions that whenever you evaluate, even if there is a point of discontinuity, it still can be evaluated. So that's where your error will come in because improper integrals are really said to be improper even if they can be evaluated. Evaluated in a sense nga may answer ka din nga makuha si ma-answer ka dayon nga convergent siya. Pero improper siya, hindi siya proper integral, even though the limits are not infinity. Okay, so I will proceed. So this one is divergent and there's no need for it to be evaluated. Okay, amo ni siyang ginamba kung a warning ka. So, then we might have the following erroneous calculation. Kung kin-evaluate mo gid siya bala o ln, so substitute mo ang answer mo ln of 2. So this is wrong because the integral is improper and must be calculated in terms of limits. So you may have a multiple choice question later on and this one will come as an answer and you will say, okay, it has an answer, but it is an improper integral. And it has to be, as it says here, evaluated or calculated in terms of its limit. So, kung ang bottom line class, kung hambalong ko sa aton language, sa vernacular, dapat hindi ln of 2 ang answer. Ang imo answer, Gudya, it cannot be evaluated. If it's found on the choices, it cannot be evaluated because one of the integral equivalent of this is divergent already, or your function has a point of discontinuity. That's the common mistake that is committed by students who does not check whether the given definite integral is improper or not. So what I'm trying to say here, before you evaluate a given definite integral, check first whether, number one, if it's improper in terms of the limits here, or whether it's improper because it has a point of discontinuity. So mabalaan mo lang na kung may point of discontinuity kay hindi na mag-exist ang function. Okay, class, I have a cola. I need to take this one. Just give me a few minutes. I will just pause recording. Okay, so we are now here. Where was I? Let me check. Sample. Okay, this is where we ended. Okay. Suppose we have not noticed that the asymptote is x equal to 1, example 6, and had instead confused the integral with an ordinary integral, then our answer would be wrong. So from now, whenever you meet the symbol, this one, you must decide by looking at the function f on the designated interval, whether it is either an ordinary definite integral or an improper integral. So sample 7, we have 4 minutes left, class. So I will finish this by Wednesday. So we will just have a class on Wednesday. Okay, I cannot finish it today. And you will have your quiz next week on Wednesday because I need to have a class on plane areas next week. Okay? And probably I may have the recordings ahead if we cannot finish everything, because if you could see, there are around 5 or 7 sets of PowerPoints and they are still coming for entered. And since we have a lot of cancellation of classes, we cannot finish everything. So we'll see, class. I will just make sure that all the recordings you will have a copy, or you'll have a link copy. That way you can listen to the discussion. Because if I will discuss this one, there's only 3 minutes left. It will not be finished anyhow. Okay? I will stop sharing now. Do you have any questions so far as to what we have just discussed this afternoon? I will just again check the attendance. Do you have any questions? So there were around 8 who are not present. Actually, more than 8 because I have 2 Kyle. Okay, 1 only. Any question, class, so far?